Hello, everyone. Welcome to Geology 106. Today we're going to be talking about the geology of the oceans. So we are going to be starting at 3 o'clock, and the time is currently 2:52. So we'll just kind of wait for some people to hop on for lecture, and then we will get started at around 3. So you can see my messy room in the background. But yeah, how are you guys doing today? Let me know in the chat. Let's get some computer stuff set up. I'm curious how many people will join us today for lecture. Not anticipating too big of a crowd today since we are indeed meeting on kind of an off day due to the exam. But I think that people may prefer this over doing like lecture right after an exam, even though we had the time to still do it right after the exam. I know as a student, I preferred not to take my have lectures the same day as my exams. It just wasn't super fun. I don't know. I felt like my brain was fried by that point, and I was just like, I can't focus. Focus is gone for today. I don't have any fun props for today. Unfortunately, I might dig out some of my rocks here to show for some of the seafloor stuff, but I'm sad because I don't have a lot of, stuff to show today. But for the thumbnail, I did find this Finding Dory sticker book I bought for myself. I did not buy this for a kid or anyone else. This is for me. Anyone else a fan of Finding Nemo or Finding Dory? Or just Disney movies in general? Or is it just me? Oops. Echo says that she's a fan. Loving it. I think I was in high school when Finding Nemo came out, and my parents actually went to go see it with me, and that was enjoyable. I think, let's see, my brother probably came too. All right, so in about 4 minutes, we will start. Let's see how many of you guys are tuned in to the lecture slides. I'm definitely going to recommend for you guys to pull up the actual lecture on your computer while we're going through this, because there's a lot of moving images, a lot of GIFs in there that really help to illustrate and depict some of the things that we'll be looking at. And it's a lot easier to just see it in motion rather than trying to explain it. So I'm definitely going to recommend pulling that up if you guys have access to it. Noah gives a thumbs up. Is the thumbs up for the PowerPoint, or is the thumbs up because you also enjoy Finding Nemo, Finding Dory? Or is it because you have located the PowerPoint? Checking my email there. Because of how you are. Oh, good. That's good to hear. My computer's making lots of whirring noises, like it's too warm. Did everybody find the lecture slides okay? I see at least one person on there. Good. So, let's see. You don't really talk about erosion, says Noah. We will talk a little bit about erosion in the oceans in this lecture, but not too much. We haven't really gotten to too much about erosion. We kind of talked about erosion, and I called it weathering for when we went over sedimentary rocks and how you break rocks down. And weathering really is like a form, it really is erosion. In terms of like large scale erosion though, like mass wasting and stuff, we're actually going to have a whole week dedicated to, well, I suppose a whole week, half of a week dedicated to erosion in terms of like landslides and things like that. All right, so the time is 3 o'clock. Let's go ahead and get started with today's lecture. I'm going to try and speed up the pace a little bit because I know that my lectures, the pace isn't super fast, and I'm trying to like work on my speech skills to improve that. We'll see how well I do though. So let's go ahead and take a look at those lecture PowerPoints. Link is on Canvas in the module for this week. Is the second midterm tomorrow? No, the second midterm will be, we're going to do 3 more weeks, and then we'll have the next midterm. So we're going to cover oceans, we're going to cover volcanoes, and what was the other section that I lined up? The order is a little bit arbitrary. There's only some things that you have to do set in stone before the other one. Mass wasting, landscapes fashioned by water. So we'll cover those 3 topics, and then we'll have our next midterm. So not for a few weeks. Deserts and glaciers are going to be following that. So deserts and glaciers and earthquakes will be the last 3 topics that we go over, and then we'll have the final. So we're going to be doing oceans this week, volcanoes, mass wasting, and then we're going to do earthquakes. We're going to do glaciers and deserts. I call the glaciers portion the cryosphere just because it's a bit more of an encompassing term, and we're going to cover more than just glaciers. We're really going to talk about a few other things. So yeah, I'm planning at least on doing deserts at the moment, but that could change. We'll see. That's like the last week of class, so we still got some time to make some decisions on that. All right. So let's go ahead and get that PowerPoint pulled up, and we will start talking about the world's oceans. The world's oceans actually cover a huge portion of the Earth's surface. They cover 71% of the Earth's surface, and then continents and islands make up the remainder of that. And the crazy thing is that up until like about 100 years ago, what lied beneath the oceans was a complete mystery. That's just crazy that we've only known what's below the seafloor for about 100 years. However, starting around like the 1940s and the 1950s, maybe even a tad earlier, we started getting a lot more new technology to help us be able to explore as well as image the ocean floor. We talked a bit about that in plate tectonics, and plate tectonics is going to factor into this lecture quite a bit. And we also developed the technology for like autonomous submersibles and a lot of satellites that allow us to help image that ocean floor as well as explore remotely. So moving on to slide 4 there. Oceanography. The definition of oceanography is the study of all aspects of the world's oceans. So it is just the study of every aspect of the world's oceans. And you can actually take an oceanography class at this community college. Steve Grubb teaches oceanography, and so does Billy. Why am I blanking on Billy's last name? I'm so sorry if you're watching this. And we also have another instructor, Billy, who teaches oceanography from time to time. And I can't recall if Al Friedman is planning on teaching that in the near future. So also it's worth noting that we have two hemispheres of the world, right? We have the northern hemisphere and we also have the southern hemisphere. And it's kind of interesting that the northern hemisphere is primarily where all the land mass is. And the southern hemisphere has a lot of ocean and not a lot of land mass. And so we call the northern hemisphere the land hemisphere, and then we also call the southern hemisphere the water hemisphere for that reason. Then moving right along to slide 5, there's 4 main ocean basins. So ocean basin being kind of like 4 main subdivisions of the world's oceans. We have the Pacific Ocean. There's more subdivisions of oceans here, but these are just kind of the 4 main ocean basins. The Pacific Ocean is the largest, right, with the greatest depth as well. And that is the ocean that is here off of the coast of our own home sweet home. The Atlantic Ocean, which is on the other side of the United States between the Americas and Europe and Africa. And it's about half the size of the Pacific Ocean. So not quite as large. And it's also not as deep as the Pacific Ocean. We also have the Indian Ocean, which is slightly smaller than the Atlantic Ocean. And most of the Indian Ocean is located in the southern hemisphere. And then the fourth main ocean basin is the Arctic Ocean, and that is about 7% the size of the Pacific Ocean. So that's just kind of a brief overview there for oceans. And then we're kind of going to, I apologize, skip over part of this chapter where we talk a lot about like ocean water and kind of temperature, right, and such. We're really going to be sticking, since this is a geology class, we're really going to be looking more at the geology of the oceans. Favorite ocean, the Pacific Ocean. My favorite ocean's the Pacific Ocean because it's home. It's the Ring of Fire, you know, yeah. So do you guys have a favorite ocean? Go ahead and leave a comment if you happen to have a favorite ocean. So, but in terms of talking about ocean water, we're briefly just going to mention, you know, like what's in the water. Is it just salt water? Well, there's a little bit more in there besides just salt, right? And there's a diagram there on both slides 6 and 7, same diagram on both slides, that shows kind of the breakdown of what's in ocean water. Most of it is indeed water, and then the rest of it isn't just table salt, but we call it salts, right? And the basically salts are kind of the total amount of solid matter that's dissolved in the ocean water. It's kind of our definition for salinity and what we're talking about when we refer to these salts in the ocean, right? And there's several different things. There's a breakdown on that pie chart there. Salinity is also typically expressed as a percent. And also dissolved substances in seawater are in much smaller quantities dissolved substances that are in seawater in like those really tiny quantities. We will express that in parts per thousand. And you'll kind of see that with in the percent symbol where it looks like the percent symbol, but there's like 2 extra little dots or circles on the end of it. So most of the salt though in seawater is sodium chloride. So let's go ahead and move on and talk about some of my favorite parts to talk about in the ocean, which is the provinces of the ocean floor. So there are 3 main provinces of the ocean floor. They are continental margins, deep ocean basins, and mid-ocean ridges. And we're going to spend a lot of time on each one of those 3 provinces. And there's a bunch of sub-features in each of these provinces. The continental margins, there's even 2 types of continental margins, the deep ocean basins, as well as the mid-ocean ridges. So that's why we're going to be spending a lot of time unpacking those 3 different provinces. Yeah, not to mention trenches. We will talk about trenches indeed. Crazy places. So continental margins. Let's go ahead and first start chatting about that. So continental margins are the outer margins where the continental crust transitions into oceanic crust, right? So let me grab a whiteboard here and draw a little sketch for you guys. Let's see. Let me get this. This whiteboard does not want to erase very well. Let's see, maybe I will grab a different whiteboard. All right, let me see my other one back here. Oh, that one erased much easier. That's a little bit better. So let's draw a quick sketch for you guys about what I'm talking about. So continental margins being those outer margins where the continental crust transitions into oceanic crust. So you've got this nice big continental crust here, right? It's thick, it's not as dense. And then you get down into oceanic crust, right? Let's see if I'm still in frame here. So we have this nice thick continental crust, right? We got our little trees there. We have oceanic crust. So we talked a lot about plate tectonics, and this is where things can get a little bit confusing. Recall that this transition doesn't always occur on a plate boundary, but it is the transition, whether or not there is a tectonic plate boundary here. It is that transition between the two. That's what we call the continental margin, kind of this transition area here. And it's also on the previous slide, on slide 8, you can kind of see them breaking up the continental margins, right? You can see the little division there. So it is that transition zone. And again, hint, spoiler alert, what that continental margin looks like is actually going to be dictated by plate tectonics and what happened in the history of plate tectonics, because the morphology of what this transition looks like greatly depends on, is it on a plate boundary? Is it not on a plate boundary? What's the history there? So that's going to dictate. And we have thus two kinds of margins. We have passive margins and we have active margins. Active margins are where you do have a tectonic plate boundary there. So let's first talk about passive margins, though, where there is not a plate boundary. There's very different features and very different morphologies and tectonic settings that occur as a result. So let's go ahead and look at slide 10 there. And this kind of shows what I'm talking about on slide 10. That map there showing kind of the larger tectonic plates. And it also shows where the continents are. And you can see that the tectonic plates all have both continent and ocean on them, except for the Nazca plate. That guy's sitting out there. And the Pacific plate has very little landmass on it. It doesn't really have a continent on it. But you can see that most of them do have continents on them. And you can also see that those black lines representing the plate boundaries don't exactly match up with continent versus ocean. You can see that some of the continents do have a plate boundary right on the edge of them, but there are other parts of that same continent that don't have a plate boundary and yet still transition into oceanic crust. So you can have two types of crust on the same tectonic plate. So passive margins are going to be those ones where they're not at plate boundaries. Moving on to slide 11, passive continental margins. They are found along most coastal areas that surround the Pacific Ocean. And again, that has to do with the fact of plate tectonics. Because the boundary for the tectonic plate, right, is in the middle of the ocean. I don't think I want to draw this. And essentially, the continents kind of came apart right there. So you have this very interesting morphology created by the fact that there was a supercontinent, Africa and parts of Europe, right, and South America and North America were all kind of one large landmass. And then a rift opened up and they split apart from each other, not towards, but apart from each other. And that creates a passive continental margin, right? So these are ones that are no longer on the edge of a plate boundary, as we've said like a million times already. Sorry, got to drill that one home though. And they experience little volcanism on those continental margins, and they also have very few earthquakes. Why apart? Can you clarify your question a little bit more for me, Alicia? So, and the reason why they experience little volcanism is because there isn't a tectonic plate there. And tectonics really drives a lot of the partial melting in the mantle that allows for volcanism to occur, or it occurs at like thinning, spreading centers, right? Where you have crust coming apart and the mantle becomes very close to the surface of the earth, and volcanism can occur that way. You don't really have either of those settings going on. Let's see, plumes and convection, I'm guessing. Oh, it says, I'm curious why the plates moved in the direction they did. You're guessing that plumes and convection are involved. That's actually a very high level question, why the plates moved apart from each other. And I also believe that it's got to have something to do with the convection in the mantle, but I'm actually not really sure why at some points, you know, things are kind of coming together, and why sometimes they rip apart, and sometimes they even like stop ripping apart, and they're like, you know, a rift zone will sometimes become a failed rift zone, and it will just stop rifting. So I'm not sure exactly what happened in Earth's history though, and what happened with the crust and the mantle to cause that. But that's a very interesting question. That's probably like a PhD dissertation question right there. Sorry, I know I don't have a satisfactory answer for you. But again, these passive continental margins form when you rip apart a crust. That's what gives rise to these, no pun intended, gives rise to these morphologies along passive margins. All right, and Noah also talks about hotspots there. We will talk a little bit about hotspots too later. So moving on to the next slide, slide 12, we can see kind of the breakdown of a passive continental margin. We have these different subdivisions. So again, I saw that it was mentioned in the comments, also called the continental shelf. And it's really important in geology, we do separate those two terms in geology and oceanography. So the margin is like the whole transition from, you know, land all the way down to the deep ocean like basin and such. And we actually reserve the term shelf for a particular part along that transition. So the continental shelf is really a extension of the continent. If the world's oceans were lower than what they are now, we kind of have a higher, we have a lot of water in our oceans right now. There have been times in Earth's history though, where, you know, we've had ice ages, and the ocean level, sea level has been lower. However, we kind of have a higher sea level going on right now. And because sea level is higher, we've submerged part of the edge of our continents. And that submerged portion of the continental crust, we call the continental shelf, right? It's very flat. And then from there, there's somewhat of a steep drop off. And we call that the continental slope. And we'll go more into this, and I'll give you guys more kind of things to write in those like bullet point areas. And then we also have the continental rise, which is not like a steep drop off. And then there's some extra little features that we get that are labeled on that diagram, and we will chat about all of those. I think we'll chat about, yes, we'll chat about all the ones that are on there. Oh no, we won't talk about shelf break. Sorry, guys. So moving on to slide 13, I have a picture here of the United States from Google Earth. And the reason why I wanted to show this is because you can really see this on the east coast of the United States, which we're familiar with. You can see this beautiful continental shelf on the edge of it. And it's that lighter blue area there off the coast of the East Coast, right? And all around Florida and parts of the Gulf of Mexico. So you can see just gorgeous textbook, beautiful passive continental margin in an area that we are familiar with, at least somewhat geographically, even if we haven't been there. So looking at slide 14, passive continental margin features. So again, like I just said, we've got that continental shelf slope and rise, right? And then additionally, we also have submarine canyons, as well as some other features. But those are kind of the two that are highlighted on this slide here. And I've also included just another diagram there depicting the continental shelf slope and rise, and then that transition from the rise to the oceanic basin, which in that area is an abyssal plain. One good example is San Francisco Bay. San Francisco Bay isn't quite it probably has like it might have some shelf off of it. Let me go back. But there is a little bit of shelf, but not too much of a shelf on the West Coast. So talking a bit more about the continental shelf on slide 15 there, if you want to fill in some bullet points. The continental shelf, like I said, it's that submerged extension of the continent. The width of the continental shelf also varies quite a bit. As you can see along some parts of the East Coast, it narrows quite a bit. And then on other parts of like around Florida, it's just massively wide before you finally get to the continental slope. So varies in width. It also has a really gentle slope. And when I say gentle, I very much stress the word gentle because it's mostly flat and it really is a very extraordinarily gentle slope. I don't know if you guys can hear that rumbling, but that's because my home office is above the garage. So also the continental shelf in passive margins is relatively featureless. It doesn't have a lot of features. And there's also a lot of oil and mineral deposits found in these offshore continental shelves. So moving on to that next slide, slide 16, let's talk a little bit about the passive continental margin continental slope. So the continental slope, by contrast, is very steep. And it's really that true boundary between the continental crust and the oceanic crust, right? But in passive continental margins, remember, it's not a tectonic plate boundary. It used to be, though, once upon a time, right? The tectonic plate boundary, though, hasn't moved. It's stayed there in the middle of the Atlantic Ocean. And at one point, the edge of this continent, as well as like Africa and Europe, and the South America were all together, right, at that mid-ocean ridge that's still there today. But spreading has continued to occur at that mid-ocean ridge, pushing them farther and farther away from each other. But the tectonic boundary, the edge of that plate has stayed the same. It's just been like adding material building the edge of that plate even further out, if that makes any sense. I hope that makes sense. Ask me though if you have further questions about that. It's kind of a harder concept to grasp, but looking at that moving picture of the globe that I put on slides 9 and 10, where you can see that that line, that mid-ocean ridge line, doesn't move. However, more material is added to the plate as the plate spreads apart from itself. Yeah, and as a result, indeed, the Pacific Ocean is shrinking. And that's why we get earthquakes, because there's a little bit of pushing around going on over there with the tectonic plates. So that kind of does it for the continental slope. Again, it's that really steep spot. So talking about the continental rise, it's sort of a gradual incline from that really steep drop off. There's just this really gradual kind of incline into the basin of the ocean. And when I say basin, I mean like the deep, expansive part of the ocean. And why does this continental rise with a gradual incline exist? It's basically an accumulation, a thick accumulation of sediment that has come off of the continent and the continental slope and fallen down the rise and accumulated at the base of the rise. So if we didn't have erosion taking place and that transportation and deposition of sediment, the rise just wouldn't be there. So it's just a thick pile of sediment that's grown and grown over time. So also sediment deposits from turbidity currents also bring sediment to the continental rise and help build that up. And we get what are called deep sea fans. And we're going to talk about and define a turbidity current and deep sea fans in just a moment. You can see them depicted though on that diagram there in the lower left, where there's this really dark line there in the continental, in the continental slope. It's very, keeping these terms straight gets difficult. Make flashcards. So in the continental slope, you can see that really dark line. That is a submarine canyon down which turbidity currents travel and then deposit that material that is carried by the turbidity current onto the continental rise. So looking at slide 18, we have just a gorgeous depiction of a submarine canyon. I was quite happy when I found that diagram on the internet because it is beautiful and you just don't get a better depiction than that. So what's interesting about this this picture, we'll talk about it on the next slide. So go ahead and go to slide 19. You can still see that picture in the bottom left corner, and then in the bottom right, we have a more cartoon representation of submarine canyons, as well as looking further onto the continental rise. We can see some of the ramifications of the of those continental or submarine canyons. Sorry. So, what is a submarine canyon? Let's give you guys a working definition. A submarine canyon is a very deep, it's a steep-sided valley that cuts into the continental slope. So you can see there in both of those pictures that that canyon is eating into the continental shelf, right? And it's eating away at the slope. So this is an erosional process that's going on. So Noah, got your erosion here for you. So essentially what happens is erosion is taking place and the material that is eroded away is carried and emptied onto the continental rise. Some of these submarine canyons are actually extensions of river valleys. So rivers usually flow in a valley, right? And kind of create a valley as they flow. More on that in 2 weeks. And if you actually go back to slide 18, and you can look at the really large picture that I put there of the submarine canyon, the one that's depicted there, you can actually see a river emptying out into that submarine canyon. It's that erosional process just continuing. So some of those are river valley extensions, and finally, most of them have been eroded by those turbidity currents taking place, so they are continuing to be deepened, a lot of them. Let's talk about what a turbidity current is. So on slide 20 there, we kind of have a depiction of a turbidity current. I left that diagram there in the bottom right, showing those submarine canyons, because there is a kind of a purple-ish, like kind of horseshoe shaped, I don't know what you call it, like half moon kind of thing coming off of those submarine canyons. And those are these deep sea fans, right, that have all of that sediment that's been eroded from those submarine canyons over time. So turbidity currents, right? What exactly is it? The working definition for you guys is that it is a dense sediment-laden water. And looking at that bottom left picture, we kind of have a depiction, right? It's underwater. We can see this cloud traveling down this gray slope. And that cloud it's basically a really dense mass of water that has a ton of sediment in it. It is very incredibly sediment laden. It is just chock full of sediment, and it's able to kind of flow down the side or flow down these canyons, right? And the deposits that these things make are called turbidites. And they form those large deep sea fans that are those kind of the purplish fans that you see there on the continental rise in that diagram on slide 20. So moving on to slide 21, I actually have a moving picture, a GIF there, showing a laboratory simulation of a turbidity current, so you guys can actually just see one in action. And there on slide 21, you can just see that it's the water is extraordinarily thick with that sediment just rushing down that slope. And the first portion of that GIF represents a narrow submarine canyon that this current full of sediment is traveling down. And then in the later part of that, in the last part of that GIF, you see it entering a much larger area of the tank. And you can see how that current just kind of fans out and deposits in somewhat of a fan-like shape there. All right. Yes, and we will talk about hydrothermal vents on tomorrow. So we'll get there. So we've talked a lot now about the passive continental margin, where it is no longer associated with a tectonic plate boundary. It's formerly where continents were ripped apart. Now let's talk about the other type of continental margin. We're going to talk about active continental margins. And this is home sweet home. This is where we live, on an active continental margin. So the definition of an active continental margin is continent's edge is on the edge of a plate that is colliding with another plate. So what do we get? What kind of what kind of, what would we call this in plate tectonics, where you have the edge of a continental plate colliding with the edge of another plate that's oceanic crust? What would we call that? Let's see some messages there in the chat. I hope you guys know this because we just had our exam yesterday. And we totally did plate tectonics for our exam. We can also see another moving image there on slide 22, which should give you guys a big hint as to what we would call what kind of tectonic plate boundary this is and what's going on there in terms of plate tectonics. I haven't seen anyone comment yet. I'm not going to spoil the surprise. Someone take a guess. Yes, it is a convergent plate boundary. And what's happening here is we're seeing it's a subduction zone, right? So that moving picture there is showing the oceanic crust subducting below the continental crust. And we have this all along the edge of the entire Pacific Ocean, creating that ring of fire. Yes, indeed, Alicia. The subduction zone occurs beneath the lighter continental crust. That's fair. Trying to type fast, and then there's also the lag for when people hit enter on submitting their comment and when it actually shows up on my end. There's a bit of a delay there. So you can see on this diagram here, let's see, let's go ahead and move on to slide 23 there. You can see that the oceanic crust is subducting beneath the continent. And what feature forms here? We have those deep ocean trenches when that oceanic crust subducts beneath the continent. And again, these are primarily along the Pacific Ocean. And you can see a beautiful image here on the bottom left as well, South America. And you can see the Andes Mountains there, right? Which are forming because there's partial melting occurring due to the subduction of that oceanic crust underneath the continental crust. And that creates those mountain ranges there, the Andes. But off the coast, we see very little continental shelf there. And we're primarily seeing this just really dark blue line. That's because there's an extraordinarily deep ocean trench there. Let's see, kind of like a metal shear line. Yeah, it's just really mirrors the edge of the continent there. Let's take a look at slide 24 in all of its glory. So still here on active continental margins. The question is, though, what happens to all of the sediment or even islands that are on top of that subducting plate, right? So when you have a plate subducting below the other one, what happens to all that material that's on the top of it? Or what happens if, like, Hawaii was there and you have, you know, this island formed in the oceanic crust and it subducts below? Like, what happens to the island? Well, what happens is you get an accretion, you get these accumulations of deformed sediment and ocean crust that adhere to the leading edge of the continental crust. And these form what we call accretionary wedges. And those are depicted in the two diagrams below there. They show the exact same thing, but one of them is just a little bit more detailed and has a lot more information on there about a mountain range forming, etc. But what we're really looking at is right at that edge there. The bottom left diagram is kind of just zooming in on how you get this accumulation of scraped off sediment. just sits there and piles up. And if you have like a full-on island, like say Hawaii, that just gets shoved up onto and crammed onto the edge of that continent and becomes part of that continent. We actually call those accreted terrains, and we have actually several of them here in Washington. And if you would like to visit an exotic terrain, you can go up to Fidalgo Island, right? A lot of that is ocean floor that got crammed onto the edge of our continent, as well as there's exotic terrains up there. So you can hit me up if you want more information. There's a lot of gorgeous parks up there. I wish we could like go on a field trip up there. It takes a while to get up there to like Anacortes, but it's so worth it because it's beautiful out there. And then you can put your hands on like mantle rock from the mantle, and ocean floor rocks and things. Final bullet point though on that slide 24, subduction erosion is what causes that sediment and rock there from the overriding plate to be transported into the mantle. So you do have some stuff, right, being dragged down into the mantle, right? You get some scraping off of the underside of the continental crust, and that kind of gets dragged down into the mantle. And that's what we call that subduction erosion there. So catching up with the comments, I see that Noah's talking about the Mediterranean Sea split or sits between the Eurasian and African plates. Same with the Red Sea. We do have, they are, do I want to say it's an active margin? What's being created in like the Red Sea in particular, I'm not as familiar with the Mediterranean Sea, but like what's happening in the Red Sea is the birth of a passive margin actually. If that seafloor spreading that's taking place in the Red Sea continues to occur, eventually the edge of I believe it's Africa sits on one side, and then it's kind of the Middle East on the other side. You have the Saudi Arabian Peninsula, I think it is. Oh, my geography is terrible. You have that peninsula there that's like Saudi Arabia, and then you have Africa on one side of the Red Sea. And if those two land masses that continue to separate because that spreading center in the center of it continues to like push the two away from each other and create new land mass, you'll eventually get passive margins there. So I kind of hesitate to call it like an active margin because it's not really like associated with a subduction zone. It's more the birth of a passive margin. So it's really cool that we actually have a place on Earth that we can look to see one in the process of being created. So let's go ahead then and move on to slide 25. This diagram, I believe, is in your book, and it's showing basically Washington and the entire coast of, west coast of the Americas, where you have subduction taking place. Of course, this happens elsewhere in the world. It's not just on the west coast of the Americas. It's pretty much all around the Pacific Ocean and in few other parts of the world. We see that accretionary wedge being developed. And then also we see in some areas that subduction is a bit more dramatic, right? And we end up with this really deep trench in those areas, right? Where it's a bit more dramatic. And we have a lot of erosion taking place where that subducting oceanic crust is really more just grinding away at the edge of that continent. And that forms that deep ocean trench there. So you can have kind of these two scenarios going on, right? So I'll let you guys kind of read up a little bit more on that diagram. Again, it's in your textbooks. So back to the three provinces of the ocean. We have now talked about continental margins and how there's two types and how there's different features associated with each, right? So now let's chat about one of the other three provinces of the ocean floor. We are going to talk about deep ocean basins, right? So let's go ahead and look at slide 27, right? And fill in some of those bullet points here. Let's see. Hold on a second. Oh, yeah, I left in a lot of those bullet points for you guys. Okay, I was just checking on that because I couldn't remember if I left those ones up there for you guys or not. The reason why I left those ones on there is because slide 27 is kind of an outline of all the things that we're about to talk about. It's all the deep ocean basin features, right? We have some trenches in the deep ocean basins. These are formed kind of in a bit of a different way, right? And we've got the abyssal plain, and we have volcanic seafloor structures. And those volcanic seafloor structures, there's really like three different kinds that we talk about. We talk about seamounts and volcanic islands. There's also another type of volcanic structure that we call geotes. I think that's how it's pronounced. Not my favorite word. That's got to be like another language. And then we also have oceanic plateaus. Let's talk about each of those. So moving on to slide 28, deep ocean trenches. So these are very long features that are also relatively narrow. And right here we can see a picture of the Mariana Trench. The Mariana Trench is kind of this, it is more of a subduction story, right? So we did just talk about subduction zones, kind of, they're not really part of the, it's hard to classify it as either part of the continental margin or as part of the deep ocean basin. I feel like it's really more a deep ocean basin feature, even though I kind of introduced it right in the previous slide. Again, it is a result of that subduction that's occurring, right? And these trenches, right, are the deepest parts of the ocean. Most of the trenches on our beautiful blue planet are located in the Pacific Ocean. And reason being, again, because that is the ocean that's shrinking because it's being kind of crammed from all sides. All the tectonic plates are just picking on the Pacific Ocean plate. And it's primarily because of the rifting in the Atlantic Ocean. So most located in the Pacific Ocean. They're also located at subduction zones. I already just said that. And then they are associated with volcanic activity. So normally what you get is that volcanic island arc. Japan is an example of one such island arc. And these island arcs are volcanic in nature, right? It's because of that partial melting occurring, because of the subduction of island arcs form when you have two oceanic plates colliding and converging together, and one of the oceanic plates goes below the other oceanic plate. And you get some partial melting that occurs due to that subduction. That stuff comes, so where you get volcanoes on the edge of the continents, right? Those are also associated with these deep ocean trenches, and we can see that all along the coast of the Americas. So let's go ahead then and move on to slide 29 there, the abyssal plains. Let's talk more about the abyssal plain. So remember, we're talking about deep ocean basins, and the abyssal plain is one such feature that is a part of these basins in which the ocean sits. So abyssal plains, they're likely the level places on Earth, flattest places on Earth. These areas are also sites of very thick accumulations of sediment. So I hope you guys have had a chance to watch the Earth Revealed video for this week. If not, go ahead and check that out. Probably ideally sometime between now and tomorrow's lecture. There's a part in there where one of the scientists being interviewed talks about this process that creates these thick accumulations of sediment in these abyssal plains. What's happening is a lot of sediment is delivered to the oceans by like wind, right? Wind actually does carry fine dust over the oceans, and that dust falls into the ocean and then rains down all the way to the ocean floor. You'll also have like the death of marine animals and organisms, right? Whether it's plankton that are these really teeny tiny microscopic guys, right? That are dying out, or larger sea creatures that pass away, and their remains fall to the ocean floor and get deposited down there. And especially when we're talking about things like plankton, they're very small, but their skeletons do build up over time and rain down on that ocean floor, developing this thick accumulation of sediment. And it's really more like an ooze, and we'll talk more about that tomorrow. So thick accumulations of sediment, we'll kind of dissect that even further tomorrow. And abyssal plains, this particular feature is found in all ocean basins. So moving on to slide 30 there, seamounts and geodes. Some geologist is going to watch this and be like, you're such an idiot. You're pronouncing that totally wrong. So seamounts and geodes are basically these isolated volcanic peaks where you had either a hot spot, right, or something else that was a hot spot that was creating some volcanic activity underneath the usually like the abyssal plain, and that caused, right, it was kind of the birth of a volcanic island like Hawaii, starting the formation, building up as it erupted and continued to erupt there, but didn't quite make it. So we also do get a lot of these though near oceanic ridges, because there's a lot of volcanic activity occurring along those mid-ocean ridges. These may emerge, just like I said, as islands. They may build up, right? These volcanic peaks, it's basically an underwater volcano. They may build up enough and grow in size enough that they break through the surface of the ocean and become an island. So these things also can be eroded away into kind of this flat-topped seamount, and that we call a geode, right? Or table mounts. That one's so much easier to say. And these geodes or table mounts, you can actually see a beautiful chain of them coming off of the Hawaiian Islands. And that's why I have that picture there in the bottom left corner of Hawaii. And you can actually see this chain of these table mounts and these geodes, right? Continuing off of that trajectory of the Hawaiian Islands northwestward. And then there's also like a sharp turn where they start traveling more northeast up towards the Aleutian Islands and the edge of Russia there, where those two are near each other. So let's talk about oceanic plateaus. Those are called the emperor seamounts. Yep, indeed. However, they are a part, it is believed that those emperor seamounts, I do want to also drive home this one point about those emperor seamounts. It is, though, believed that they are still related to that same Hawaiian hotspot, and that bend in the from the Hawaiian chain to the emperor seamounts just represents like the tectonic plate was once going this direction, and then it was like, nope, we're going to go this way now. Right? And that record is preserved there with those seamounts. So talking about oceanic plateaus are generated from vast outpourings of fluid basaltic lavas. So you'll get like this, actual like plateau going on. Typically, though, you don't have a lot of thick outpourings of that basaltic lava, to my knowledge. It tends to usually form more like pillows. And we will also chat about pillows in just a few slides. So now moving on, transitioning to our third province of the ocean floor, we're going to chat about mid-ocean ridges. I know we've kind of chatted about them already in today's lecture, as well as quite a bit in the plate tectonics, but we're just going to review them. And then we're also going to just dissect them a little bit further and talk about them in terms of oceanic seafloor morphology. So slide 32 there is this gorgeous illustration I am such a fan of, showing a lot of those mid-ocean ridges, and they're the really dark lines that are in those oceans there. And you can see that it kind of wraps around, kind of starting off the coast of like Greenland and right through Iceland there, going down through the Atlantic Ocean. You can see that it wraps around the southern edge of Africa, wraps around South Africa there, and kind of points up towards India, and then takes a sharp turn back down and skirts along the southern part of Australia, and then wraps back up and comes up along the side of the Americas. It's that dark gray line. So some people actually call this a mountain range, and they claim that it is the longest mountain range in the world on our beautiful blue planet. So taking a look at slide 33, another one of those moving pictures there. This is just a diagram I found it online, the History Channel made it, of a mid-ocean ridge, or oceanic ridge, or rise are some other names that it goes by. So oceanic ridge, or the, mid-oceanic rise. I tend to call it the mid-ocean ridge. When the History Channel was actually about history, right? Oh gosh. Who among the five of you who are here with me, Alicia and myself, who else is familiar with the History Channel when it used to not just be like reality shows, but when it actually used to be about like history and sometimes science as well? Anybody else out there? Oh, so relevant, so true. All right, Noah's also familiar with when the History Channel used to actually be about history. I hate the History Channel now. But then again, I really haven't watched it in like 5 years because I haven't had cable in 5 years. The internet's just better. Internet's just superior. Don't need to pay and shell out a lot for cable. So let's give you guys a working definition of mid-ocean ridge. The working definition that you can put there in that bullet point above that moving diagram there from the History Channel is that it is an elevated portion of the seafloor that forms a broad linear kind of swell, right? Aha, Echo is also familiar with, back in the day, the OG History Channel. So slide 34 there, we're going to kind of dissect this a little bit further. Mid-oceanic ridges are characterized by an elevated position of that oceanic crust. They're also characterized by a lot of extensive faulting. So looking back, this slide doesn't really show the extensive faulting so well. I was really torn. I almost put the other moving picture on this slide, but it's on the next one. You can see that extensive faulting quite a bit better on the next slide that we'll look at. And also there are numerous volcanic structures that have developed on this newly formed crust, right? There you can kind of see on this diagram some of those outpourings of lava, right? That are solidifying and turning into stone. And you can see that that is what causes the new continental crust, not just the solidification there, like at the surface of these mid-ocean ridges, but also like in the deeper down, right? Below the surface of the crust. And they're also characterized by layers of basaltic rock, our good old friend basalt. Who remembers basalt from last week? You guys have some in your kits. I'm not sure what number it is. I don't have my key pulled up, but you guys know what number it is. I hope. Where's my basalt? I don't know where that one went, but I have one right here. So good old basalt here. So you get layers and layers of basaltic rock. Why is it basaltic though at the ocean ridges? It's basaltic because the mantle is primarily mafic, right? And it's a nice mixture of all of this stuff, right? Number 9, thank you. So number 9 in your kits, guys. If you have the larger kit like myself, I gotta find it. Number 11 in the larger kit is the basalt. And mine has a lot of holes in it. I don't know if you guys can see that. Yeah, mine has a lot of holes in it because this formed not in the ocean, right? But here's another one that doesn't have as many holes in it. We looked at this guy last week. I wish I had a sample of what it looks like when it forms in the ocean. It's really crazy. Anyways, layers of basaltic rock. That's the last bullet point there on the oceanic ridge system. I didn't finish my point. Sorry, guys. Attention deficit disorder. So why is it basaltic? Why is it basaltic? It's because you have mafic material there in the mantle. So the first minerals that form out of a magma, right, and out of a mafic magma especially, right, you're going to have the olivine and the pyroxenes, right, and the plagioclase forming out of that. And that is what defines basalt. That's the definition of basalt. So that's what forms there at those mid-ocean ridges, as well as, things like, peridotite and dunite. More on that in 2 slides. So let's go ahead and look at slide 35, the elevated position of the ridge, right? Why is that position? We've mentioned that, the ridge is elevated. Well, that's due to that hot, less dense material that's forming on the edge of the crust. So that newly formed crust is a little bit less dense. It's not as dense as the other stuff. And it's also hot. So it's because it's less dense, it doesn't, sit as low, if you will, on top of the mantle. It's a bit more buoyant, just kind of similar to how the crusts are extraordinarily buoyant, but this is just a little less buoyant, so it rises up a bit. When it cools, though, it contracts and it becomes denser as it moves away from that oceanic ridge. And that density, that change in density because of that contraction that took place during cooling is what allows it to then sit a little bit lower on top of the mantle. And again, the mantle, I haven't gone over your test yet, but I'm probably going to do that tonight. I'm probably going to be working tonight. I hope you guys got this. The mantle is still like solid, but it's just like squishy and malleable. So denser stuff kind of sits lower in that mantle, right? Kind of compresses down more than something that's a little less dense. So let's go ahead and look at slide 36. Stay with me here, take some notes, because this is not in your books. But I want to go over it because as a geologist, it's really hard not to talk about this. It's rocks. I love rocks. So let's take a closer look at the oceanic crust itself. And we're also going to be talking about it developing along the mid-ocean ridges there. So remember when I said that this basalt isn't quite what it looks like at the surface of the mid-ocean ridge usually. And I'm also not really, I guess it does form kind of on the surface of probably those large ocean outpourings because I don't see how it wouldn't. It forms what's called pillow basalt. So on this diagram, you can see kind of the cartoony colored diagram on slide 36. You see that there's some ocean sediment buildup there, right? From the raining down of materials through the ocean, whether that's the skeletal remains of plankton or larger creatures or dust that was blown over the ocean and has sank down to the ocean floor. But what we have actually, and you can see that there's less of it near the oceanic ridge. That's because that stuff is new. And it hasn't had as much time to accumulate stuff, right? And further away, it's been there a while. It's a little bit older. It's a little bit more mature. It's had some time to, reminisce and grow up a little bit. And it's gotten some more accumulation of sediments on top of it as a result of being around a bit longer. But the magma that's coming up at those mid-ocean ridges, right? Because we've got that partial melting going on there, the mantle. That magma close to the ocean water, when it comes in contact with the ocean water, it forms these like pillowy blobs, right? And you can see a picture of that on the left-hand side of slide 36 there. These gorgeous pillows. You can actually see some of these in Eastern Washington. If you're curious about that, I can send you some resources. If you are like, I'm going on a drive through Eastern Washington, I want to see some pillow basalt. But that wasn't formed in an ocean. It was formed more in like probably lakes. So just any time that you have a mafic magma erupting into a body of water, it's going to form these blobby pillows, and we call it pillow basalt. Right? And then below the pillow basalt, when we're not so much, really in contact with the cold ocean, we get these, it's still basalt, but it kind of forms more in these like sheeted dikes, right? And you can see I've kind of illustrated this up and down kind of feature there. And then below that, because we are now deeper in the crust, it's a bit, warmer, because we're getting deeper down into that crust. The magma that's there cools slower. And what happens when magma gets to cool slowly? We form these big crystals, right? And large enough to actually see, unlike basalt. So same magma as this stuff, but cools slowly as opposed to quickly. So we actually get to see the crystals that make this up, and we get the rock gabbro, right? Same chemical composition, same minerals, just bigger because it cooled more underground, right? Where it's warmer and it had time to like think about things as it was cooling off rather than just like this sudden, oh gosh, it's all got to take place like right now. I don't have a lot of time to think about this. I'm just going to make really small crystals because I don't got time. Whereas this one, like the crystals got to like grow out of the melts and then more of it slowly kind of cooled off a little bit more and then you formed the next crystal, right? So you got really big, large crystals in there. Below that, there's actually the mineralogy changes a little bit, and we have kind of dunites and periddotites going on there. It's more ultramafic down there. This is mafic stuff, and now down at the deepest part of the oceanic crust, we're getting into ultramafic. So we have primarily like olivines and pyroxenes. We've left out the plagioclase and other things. And I do have a sample of dunite here. It doesn't quite look exactly like the one that's I've pulled offline. There is some variation that occurs. All right. So this is a dunite here. You can see that it's kind of greenish, right? Lovely rock. It would probably make a very beautiful countertop or mantle. Haha. Pun not intended. Someone told me that I make a lot of geology puns, but I don't notice when I'm doing it. It just happens naturally. So that is what we call this whole system here, this whole kind of top to bottom crust, oceanic crust, where we transition from pillow basalt to sheeted dikes, to gabbro, to dunite. And then below that image, it's cut off, but you would get into just mantle, right? And the dunite peridotite is really, this is really like mantle material. So below that is the transition into that mantle material, the dunites and the peridotites. And we call that whole kind of, you think of it like a cake. We kind of call this whole cake the ophiolite suite. So let me type that into the chat too, because I realized I didn't actually put it on the slide. All right. So ophiolite suite there. And you can actually, again, up in kind of the Anacortes, as well as Deception Pass, Whidbey, North Whidbey Island area, you can actually see rocks that are part of the ophiolite suite that were indeed oceanic crust, right? They're not pretty necessarily, like they don't quite look like this guy. They don't look like this anymore either. Or even this, or the sediment, but you can actually find that oceanic sediment. It's been through it. It's had a rough time going from the ocean floor up to the continental crust. And in going through it and kind of having a rough time, it's been metamorphosed. They're now more metamorphic rocks, or they're just really chewed up. So you can find gabbro up there, but it's just not this pretty. It's been somewhat altered due to being exposed to the elements. This is a really fresh sample. Hasn't been around for very long. Wasn't exposed to the elements and weathering processes if at all, before it came to us. Whereas up there, it has been. But it's still kind of interesting, just the fact knowing that you can actually travel to locations here in our own states, like an hour and a half away or less, and actually see this stuff and be like, this was once part of the ocean, and now it's here, part of my state. All right, so let's go ahead and conclude lecture there. We will talk about ocean sediments tomorrow. And we went through a lot of material today because tomorrow lecture is probably only going to be about an hour long, I'm hoping for. So yeah, we got through a lot of good stuff today though, and we'll talk about ocean sediments tomorrow. Your lab is also about ocean sediments. So tomorrow's lecture will be kind of helpful there. However, I believe that all of the background material that I've written in that lab should be pretty sufficient if you want to get started on that now, even though we haven't had lecture about it. Also, again, keep in mind those Earth Revealed videos. Keep giving those guys a watch. Interesting name, yeah, Ophiolite. Reminds me of like Ophelia from like Shakespeare. So, any other announcements? Yeah, I'll try to put in a few extra hours tonight to get your exams graded. And if not, though, soon, because I like to grade exams fairly quickly. Any other questions, though, comments, concerns that you guys have before concluding today's meeting? 5 of you guys that are here that joined us on this Tuesday rather than Monday. Live chat, please. Okay, so I'll do a Google Hangouts with Noah. Does anyone else want to also join the Google Hangouts? Let's see. Oh, Alicia raised her hand prior and I didn't see that. Let's see. Oh yeah, I didn't even realize that you guys could see your grades for the exams yet. Yeah, a lot of the questions for the exam, I have to go in and grade. Only a few of the questions have, for example, the multiple choice, where the software, the Canvas software can just grade that automatically, as well as some of the fill in the blanks, provided that it even like, if you capitalize something and I didn't add like capitalization in there, I have to go in and add all the possible variants for the multiple choice that you might type in there, and they don't factor in things like capitalization. So for all the fill in the blanks, I have to be like oceanic crust capitalized, oceanic crust with a period at the end of it. And if I don't like think of everything that you guys might type, or if you misspell something, it'll be like wrong. So I have to go back in and grade all of that. Yeah, everyone's scores are in the high teens right now, I think, just because that's all that the software itself can really do. So if your score is in the high teens, that's not your final score. Everyone's is like in the high teens right now. So don't panic. Any other questions, or anyone else want to hop in on the Google Hangouts session that I'm about to start getting that Google Hangouts set up while I wait for some more chats to come in. Yeah, have a great evening, Alicia. I'll probably let it go for about 1 more minute for that delay time, because I have no idea how long the delay time really is between when you guys hit enter and when it shows up on my end. I know that to you guys, it probably looks like it shows up right away because you hit enter and it's right there. But on my end, it doesn't show up right away. Have a good evening, Echo. All right, it's been about a minute. I've sent an invite to Noah. And so I'm going to turn off the live stream for now. Have a great rest of your day, and I will see you guys back again tomorrow for more talk about the oceans. Hi, Noah.